So now that we have this definition of torque and we have this entire sort of toolkit, let's put it to use in some sample problems. So in this problem, we have a figure which is showing a uniform disk that can rotate around its center like a merry-go-round. The disk has a radius of 2.0 centimeters and a mass of 20 grams and is initially at rest. Starting at time t equals 0, two forces are applied tangentially to the rim as indicated, so that at time t equals 1.25 seconds, the disk has an angular velocity of 250 radians per second counterclockwise. Force 1 has a magnitude of 0.1 newtons, and we're asking about what the magnitude is of force 2. First thing we want to do is find what the moment of inertia for this kind of disk is. And if you want to look it up, you're welcome to do so, but you can take my word for it. The moment of inertia of this sort of disk rotated about the center is 1/2 mr squared. All right, so to go about solving this problem, the first thing we want to say is, what's our definition of torque using Newton's second law when it's applied to a rotating disk or to some sort of circular motion? So torque is equal to moment of inertia times the angular acceleration. The next thing that we say is, what is that torque? What is that? Well, we know that it is R1 here. That would be, or sorry, R2 and R1. They're the same. R2 and R1 are identical. So RF2 sine 90, why 90 degrees? Because this force is being applied tangentially to the radius, minus RF1 sine 90 degrees equals 1/2 mr squared alpha, and that is just substituting in this moment of inertia into this expression. You may be asking yourself, okay, how do we know that this should be positive? RF2 is positive and RF1 is negative. Well, notice that the torque that's being applied from force 2 is tending to rotate the disk in this counterclockwise direction. And the counterclockwise direction is the positive direction, whereas F1 is tending to rotate the disk in the opposite clockwise direction, F1, and that's going to be negative. So that's why this expression, RF1 sine 90, is negative. That's a negative torque, and then F2 in the opposite direction is a positive torque because it's rotating this thing counterclockwise. All right. So then what we can say is a whole bunch of things are going to cancel, or at least a few things are going to cancel. So we know that sine of 90, that's equal to 1. So that helps us kind of tidy up this expression quite a bit. We have an r here, and one of these two r's, they're going to cancel. If you divide through by r, the r's drop out. So we're left with F2 minus F1 equals 1/2 mr alpha. Okay. Now, the next thing that we're going to want to do is substitute in for alpha in terms of omega. We're given what omega is at the final, what the final angular velocity is. We're told what the initial angular velocity is as well, and that's going to be 0. So that's from rest. Pulling this equation out of the big 5 equations that were discussed in the previous chapter's notes, if you're wondering where that comes from, I refer you to the previous chapter. The acceleration in this case is going to be constant. Force is constant, so acceleration is constant. Force is not a function of time. So we can use those big 5 equations to say omega equals omega naught plus alpha times t. Omega naught is 0 because, again, we're told that this is starting at rest. This allows us to solve for alpha. And once we've solved for alpha, we can then plug that expression in up here. And what that's going to give us is an expression for the difference in forces in terms of the final angular velocity and in terms of the final time, both of which are quantities we know. So F2 minus F1 equals 1/2 mr omega over t. We rearrange this. We find that F2 equals F1 plus 1/2 mr omega over t. Well, we know what all of this is, so we can go ahead and plug in. F2 equals F1, which is 0.100 newtons, plus 1/2 times the mass of the disk, which we're told is 20 grams. So that's 0.02 kilograms. Then we're looking at a disk with a radius of 2.0 centimeters. So R is 0.02 meters. Okay. We know what the final velocity is, and that's 250 radians per second. So we put that up here, and then we divide that by the time t of 1.25 seconds. So 1.25 seconds goes in the denominator. We go ahead and evaluate, and we find that F2 is equal to 0.140 newtons. Okay, so that's a nice kind of simple example of the use to which we can put the idea of torque. Let's take a look at something which initially might not seem like a rotational problem, but which actually is, which is that of a seesaw, the problem of a seesaw. So let's have a look. The figure below shows particles 1 and 2, each of mass m, attached to the ends of a rigid massless rod of length L1 plus L2, with L1 and L2 defined as shown. So we have a mass 1, and it's some distance L1 from this fulcrum. And we have some mass 2, and that's distance L2 from this fulcrum. L1 is given as 20 centimeters, L2 is given as 80 centimeters. The rod is held horizontally on the fulcrum and then released. So what we're going to imagine is that there's this rod, and it falls on top of this fulcrum. Eventually it's released, and the rod will slip off of that fulcrum. So it's asking us for the magnitudes of the initial accelerations of particle 1 and particle 2. So what it's asking for is magnitude of the linear acceleration 1 and magnitude of the linear acceleration 2. How exactly we're going to solve this? Well, one thing that would be handy to note is that the linear acceleration is equal to the radius times the angular acceleration alpha. And angular acceleration alpha is something that we can solve for using this concept of torque. So the net torque is equal to moment of inertia times the times the angular acceleration. So our goal is to solve for this guy, solve for alpha, and once we've solved for alpha, we can solve for acceleration. So that's kind of where this problem is going. How are we going to do that? Well, first we want to find what the moment of inertia actually is. And in this case, because the rod here is massless, we're only concerned about mass 1 and mass 2 separated at some distance from the point of rotation. So there's no mass here, we don't need to use an integral, and there's no mass here, so we don't need to use an integral. We're told that the rods are massless, and the moment of inertia is equal to MIRI squared. And again, that should be squared. That should be made a little bit more clear. Okay, so what we can say is the moment of inertia is equal to M1 L1 squared plus M2 L2 squared. I believe that the masses are said to be identical in this case, so we can just refer to that as M. Yeah, I think the problem says that the masses are identical, so we can just refer to it as M. And again, M times L1 squared plus M times L2 squared is going to give you the moment of inertia. We go ahead and make the substitution for moment of inertia to the right side of our torque equation. And then we say, okay, what is the net torque? The net torque is going to be F times R times sine of the angle at which the force is applied. The force in this case is gravity. That's W. That's pointing straight down. And that's applied at a right angle. And as it's applied at a right angle, that's where this sine of theta is coming from. L1 is the length of the lever arm here in this left half of the problem. mg is the magnitude of the force. It's the weight that we're taking a look at here. Once again, you might be asking yourselves, why are the signs arranged the way that they are? Well, what we're looking at is the force that's acting on particle 1 is moving it this way. And because the force that's acting on particle 1 is moving it this way, moving it in a counterclockwise direction, and by convention that is positive. Whereas the force acting on 2 is moving it in a clockwise direction, which by convention is negative and negative torque. Okay, so we go ahead and we say this is our expression for the net torque. Right? So now that we have this equation, we can go ahead and do a little bit of simplification because the masses are identical. This mass, this mass, this mass, and this mass will all cancel. And we're left with the greatly simplified L1 minus L2 times G equals L1 squared plus L2 squared times alpha. Where's the sine of 90 go? Well, sine of 90 degrees is equal to 1. So we can just, carry on from there. And now what we're able to do is come up with a nice expression for alpha. So we just bring this guy over to the other side of the equation, and we have alpha equals L1 minus L2 times G over L1 squared plus L2 squared. Okay, and we know what L1 and L2 are, and we know what G is, because presumably this is happening on Earth, and we find that alpha is equal to negative 8.65 radians per second squared. What exactly does that tell us? Well, that tells us that the rotation is going to be in this direction. So it's going to be a rotation in a negative clockwise direction. That makes a certain intuitive amount of sense. I mean, if I've got, a pencil or something and I drop it so that it's, not evenly balanced, you're going to expect rotation to happen in the direction that's got more spinach on it, more mass, basically. Or not necessarily more mass, it's got a longer lever arm. The longer lever arm is going to be the side that falls and therefore rotates in this clockwise direction, which is negative. But again, we're trying to find these two magnitudes. So what we can then do is say, all right, magnitude of A1, so 0.1, is going to equal that magnitude of the angular acceleration times L1, or negative 8.65 radians per second squared times 0.20 meters. That's the length L1, and that's equal to 1.7 meters per second squared. And if we do the same thing and we're looking at A2 instead, we have a magnitude of A2 is equal to angular acceleration times L2, and that's negative 8.65 radians per second squared times 0.80 meters, or 6.9 meters per second squared. So what exactly is this acceleration going to be, if we weren't just talking about a magnitude? It all depends on how you define what positive y is, what the positive y-axis is. But you can imagine that the acceleration of 1 is going to be in this upward direction, and the acceleration of 2 is going to be in this downward direction. Sorry, that should be A2 is going to be going downwards. All right. So let's take another example. Notice that so far in this class, we've only dealt with pulleys that have two masses on them. So what happens if you've got a pulley with just one mass? Without an understanding of how rotational motion works, unfortunately, you'd be kind of stuck. But it's your lucky day. You're going to learn how to deal with this kind of problem. Okay, so a mass m is suspended by a light string that is wrapped several times around a uniform pulley of radius r and a moment of inertia I equals 1/2 mr squared. The pulley can rotate without friction around a horizontal axle through the center. When the mass m is released, what is the magnitude of its downward acceleration in terms of free fall acceleration g? The first and most important thing to note here is that the downward acceleration is going to be less than g because this pulley has mass and it's not going anywhere. This mass here, this block, is going to be feeling basically a pull upwards, which is connected to the ceiling here. And again, this block is not going anywhere. This block is not being accelerated. So the acceleration of this system is going to be less than the acceleration due to gravity because that pulley has mass. So how do we go about solving this problem? Well, whenever you're in doubt, you should start drawing free body diagrams. So let's first draw a free body diagram for the mass. Let's define upwards as positive y. We have a force of tension that's acting upward on the mass, and the weight of the mass, which is acting downwards. We say that the sum of the forces in the y direction is equal to m times a y, the acceleration in the y direction. And ultimately, this is the quantity that we're going to want to be solving for as a sub y. So keep an eye on it. All right. So we say, what are the forces that are acting on this block? Well, there's tension, and tension's acting in a positive direction, minus mg. Mg in this case is acting as a negative direction as we defined it, is equal to may. So let's go ahead and solve for the tension, and tension equals m times a sub y plus g. Why would we be wanting to solve for the tension? Well, we want to see what the tension does to the block, to the pulley. I'm living out my Horatio Hornblower fanboyism. A pulley in nautical terms is referred to as a block. So you talk about a block and tackle. A block is a pulley. So if I refer to a block by accident, I'm referring to the pulley in this case. Okay, so let's take a look at what's going on in the pulley. We have the free body diagram looking at the forces acting on the pulley. There's an upward force from this support. You can think of it as a separate force of tension or something if you like, but it's what's keeping this pulley attached to the ceiling here. That force of support is being countered by the weight of the block itself. I keep doing it. The weight of the pulley or block itself is pulling downwards, and there's a supporting force pushing upwards. And you have this force of tension, which is also acting on this pulley system, and that's facing downwards. And then, once again, let's say that positive y is in the upwards direction. Right? What we can say is that the sum of forces in the y direction is equal to ma sub y. And we can further say that when we account for those forces, there's a force of the support, which is positive, minus a force of tension, which is negative, and minus the weight of the pulley itself. Because again, that's being, going in this negative direction. And we know that this is all equal to 0. Why? Because this body, this pulley as a body, does not accelerate. It does not peel off of the ceiling and fall down. The only thing that's falling is this mass. So we can say that the net forces in the y direction, when we consider the pulley as a whole, is equal to 0. We can then rearrange that, and we say that the force of the support is equal to T plus mg. Right? So that's nice, but how are we going to get the pulley side to give us something in terms of the acceleration in the y direction and in terms of a sub y? Well, what we're going to be looking at is the acceleration of the rope, of this particular rope here, which is going to be the same as the acceleration of the block. How does that help us? Well, as that rope is accelerating, we can measure the acceleration of this point right here, which I'm highlighting in red. And perhaps considering that the thing is in red, let me do that in a slightly different color. Let's do this in blue. We're interested in what's going on, the acceleration of the string at this particular point, which is going to be equal to the angular acceleration of this block. So even though it's not accelerating in a linear sense, this thing is going to start spinning around. That's what a pulley does. That's kind of the point of a pulley. All right. So if we look at the acceleration of a point on the edge of the pulley and the acceleration of the rope, that's going to give us something that's expressed in terms of a sub y. How do we get there? Well, first we say that the net torque is equal to the moment of inertia times the angular acceleration, and then we can say what that net torque actually is. The net torque in this case is going to be F support sine of 0 plus mg sine of 0 minus tr sine of 90 degrees. Again, why the sines? Well, the tension in this case is accelerating the block in this clockwise direction. That means it is a negative torque. Why am I saying sine 0? Well, the weight and the force of the support are occurring parallel to this radius, right? So we say that the angle between the force being applied and the radius is 0, and sine of 0 is 0. So both of these drop out, and they both become 0. How about the tension force? Well, we know that the tension force is tangential to the radius, and let me just draw that in here. So we got a radius here of this pulley, and we've got a right angle here. So we know that the torque, which is being imposed on this pulley, is the magnitude of the force T times the radius times sine of the angle between them, which is 90 degrees. And again, this very nicely simplifies to 1. Okay. And then what about this moment of inertia? Well, we've been told that the moment of inertia of this particular cylinder is 1/2 mr squared, and then times alpha. So we have this equation right here. We also know, because we've talked about it, I hope you're finding that we're talking about this ad nauseum, and if not, maybe watch the lectures again. We also know that r times the angular acceleration is equal to a sub y. So the angular acceleration is equal to a sub y times r. So again, the linear acceleration of this point right here, that linear acceleration ay, is the tangential acceleration of this particular system, and we know that that is r alpha. So we can now solve for alpha, and we say that alpha is equal to a sub y over r, and that gives us something that we can substitute. Hey, I kind of like the looks of that. We're now getting close to something that we can actually evaluate, and we have this a sub y term. And that's going to get us to the point where we can have an actual system of equations, where we're going to have 2 unknowns and 2 equations, and we can solve, and we'll be very happy. Okay, so negative tr, and again, this is 1, so that whole sine 90 business drops out, equals 1/2 mr squared a sub y over r. And again, this big R and this little r are the same. They're both in the case of the radius. And again, to keep the nautical theme going, the r's are the same. Thank you very much. I'll be here all night. So we get a couple of kind of nice results here. This is, big R here. This r cancels and gets rid of one of the r squared terms. So we're just down to 1r. Let's say that we divide both sides by the radius of the pulley, and we notice that the r's drop out. So this simplifies very nicely down to negative t equals 1/2 ma sub y. Okay. And we got this equation in red. We've got this equation in red. We've got 2 equations for tension. Tension is unknown, and a sub y is unknown. 2 equations, 2 unknowns. So we go ahead and solve using a system of equations. we can say that negative t is equal to 1/2 ma sub y. That's what comes from this left half of the problem. And t is equal to m times a sub y plus g. That's what's come from the right half of this problem. We combine the equations and solve for a sub y in terms of g. So what we say is negative m times a sub y plus g equals 1/2 m a sub y. And again, this is just changing the sign of this. We multiply both sides by -1, so we know what negative t equals. We go ahead and rearrange, and we also note that m drops out. So m drops out, and negative a sub y minus g equals 1/2 a sub y. We then find that a sub y is equal to negative 2/3 of g, and therefore the absolute value of a sub y is equal to 2/3 g. And you'll notice, fortunately enough, that the sign of this acceleration actually matches the sign of the acceleration we would expect given our definition of our axes. We expect acceleration to be that way, and that's going to be negative in this case. So it all works out in a nice, tidy way. So that concludes what I'm going to talk about in this particular lecture in part 1. In part 2, we're going to see what happens if you have not only something which is rolling, but something which is undergoing translational motion at the same time. That's just how I roll. So if you have, for instance, a ball which is rolling down a slope, the axis about which it's rotating is moving at the same time as the ball is turning, or the ball or the rod or whatever it is turning. So we're going to learn about how to do that in the next video. Thank you for watching, and I will see you next time.